Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to show how to calculate multivariable differentials. Now before I do that, I'm going to talk a little bit about just a single variable differential. So what we're looking at here is the function y equals x squared. And I like to use a nice simple function for my examples. And we're just going to kind of investigate what happens when we look at what happens to the function when we go from x equals 2 to x equals 2.5. So f of 2 would be 2 squared, which is 4. And then f of 2.5 would be here on this graph. I went ahead and calculated over here to the right. F of 2.5 would be 2.5 squared, which is 6.25, and that would be that value right here. Go ahead and label that 6.25. Now, in this example, we could call delta x 0.5 because we moved to the right by 0.5, and then the delta y would be the change in y. That'd be 6.25 minus 4, which is 2.25. So what that means is when we went to the right 0.5, y went up 2.25. Now, we've got this function y equals x squared, and we're going to take a look at this function's derivative. dy dx would equal 2x. The first derivative is a separable beast, so I can write this dy equals 2x times dx. And what I'm going to do now is put x equals 2 in here, and I'm going to use 0.5 for dx. And if we calculate this value, we get 2. Now you'll notice that it's the 2 is not exactly 2.25, but it's just a little more than 10% off. It's what I always call curiously close. Now, in the picture, the delta y is this distance. The dy, if I drew a tangent line through here, let me go ahead and do that. The dy would be this distance, and you notice that's just short of the delta y. So I'll put the delta y in green, and then the dy would be in red for the same delta x. You'll notice even graphically it's a little bit short. Now, an important thing to realize is that as long as delta x is small, then dy is approximately equal to delta y. Now in this case they differed by 0.25, but if I went ahead and made this not just 2 but maybe 2.1, this difference would be smaller and smaller and smaller, and not just smaller numerically but by percent. When I look at the difference between these two, they differ by 0.25. That's a little more than 10%. But if I dropped that delta x to 0.1, that percent difference would drop with it, and it would get small in a hurry. So this is an example of a single variable differential. One thing you'll notice is this term right here is dy dx. So dy we can say is equal to dy dx times dx. Right. Now what we're going to do here is we're going to and let me back up. And this dy is approximately equal to delta y as long as dx is small. Now I'm going to back up here and look at this in terms of more than one variable. All right, so imagine we have some function, I'm going to call it phi, which is a function of x, y, and z. Then we can calculate what are called partial derivatives for this function. And one of them would be d phi dx. Now you notice that this d is kind of a squirrely, I call it kind of a squirrely looking d. That's a notation for a partial derivative. Okay. Then we could calculate one with respect to y. So that would be partial of phi with respect to y. And again, I'll show examples of this in a minute. And then we can calculate a derivative of this function with respect to z. Now, just like in our single example where we could calculate a differential for y, let me write down what we did. We said that dy was equal to dy dx times dx. We can also calculate differentials for phi. There's going to be a differential of phi for x, and that thing's going to look like d phi dx times dx. Then there's going to be a differential of phi for y, and that's going to equal d phi dy times dy. And then there's going to be a differential of for phi with respect to z, and that's equal to this times dz. This variable then has what's called the total differential, and it's just the sum of the three differentials. So here's what it would look like. d phi, right, which stands for difference in phi or differential in phi, can be calculated by d phi dx times dx plus d phi dy times dy plus d phi dz times dz. And again, each of these terms individually is what we had before, basically. Then the total differential is the sum of the three. So I'm going to go ahead and calculate a numerical example here. Let's suppose that phi is equal to xy cubed over z. There's a function of three variables. Then the differential of phi is going to equal, all right, d phi dx. What you do now is you hold everything constant except x. So you treat this like a constant. X is the variable. So if we differentiate that with respect to x, we get y cubed over z, right? And then we multiply by dx. This is now a differential with respect to x. Next term, differentiate with respect to y. So we're going to treat these two constant. This thing's derivative with respect to y would be 3y squared. So we're going to have 3y squared over z dy. Oops, I forgot the x. 3x y squared over z dy there. This term right here is the derivative of this expression with respect to y. Next term, all right, derivative with respect to z times dz. So now we're treating z as the variable. X and y are constants. So we're going to have xy cubed. Now this is effectively 1 over z, or z to the minus 1. Its derivative is going to be minus 1 over z squared. I'm going to go ahead and put that z squared in the bottom and just change this to a minus. Right, and then when we multiply by dz, there's our differential of z. So here's an example of how to calculate a multivariable differential. This is the differential with respect to x, differential with respect to y, differential with respect to z. Now you'll notice that, plus, plus, minus. Well, that's because if we increase z, if you look at the original function, right, that actually drops the value of this function phi. The plus or minus signs are going to be somewhat optional, I guess I'll say for now. We're going to use this for estimating error. And when you estimate error in measured quantities, we're going to use the differentials here to represent small uncertainties in measured values. But you typically don't know if you measured a quantity too big or too small. So these differential variables in the context of measuring error could be positive or negative. So what we're going to do when we use this for error analysis, I'm going to save this for another video, is we will just take the absolute value of every one of these quantities, because we won't know the plus or minus signs on these differential variables anyway. So anyway, the purpose of this video was to describe what a multivariable differential is, right? It's a small change in some variable that occurs because of changes in other variables. So similar to dy is equal to dy dx times dx, like in my quadratic example, it's similar to that, other than we have to take all the variables into account. So in this example, x is taken into account. In this part, y is taken into account. In this part, z is taken into account. So next thing is just not only understanding what the differential is, but how it's calculated. And hopefully I did this right, but d phi dx means treat x constant. Treat this stuff constant, differentiate with respect to x. That's what that term is, right? Times dx. Next term, d phi dy, means treat x and z constant, differentiate with respect to y. That'd give you 3x zy squared. That's that term, and then times dy, and so forth. So hopefully after watching this video, you have an idea of how to calculate a differential. Have a great day.